rockets and artificial satellites. The first truly scientific ideas about spaceflight were given by a Russian, Konstantin Tsiolkovsky. He was regarded as the father of space research. It was his work that laid the general principles of astronautics. It was in 1926 that an American engineer, Robert Hutchings Goddard, built and flew the first liquid propellant rocket. His work was entirely independent of that of Konstantin Tsiolkovsky. Rocket engines are used for launching satellites in orbits around the Earth. Unlike a jet engine, which needs air as fuel, a rocket engine carries its own fuel and oxidizer. A rocket can therefore function at great heights where very little or no air is present. The important constituents of a rocket are the fuel, the oxidant, the pumps, the engine, the exhaust or the nozzle, the payload and the outer frame. The fuel. To help the rocket move at great velocities, the fuel must be burned at a high rate. The burning of the fuel and the oxidant produces hot gases. Both fuel and oxidant together are called propellant. The fuel may be solid or a liquid and is kept in a separate chamber. The common liquid fuels used are liquid hydrogen, kerosene and hydrazine N2H4. Solid fuels are disadvantageous owing to their weight. Oxidant. The substance that provides oxygen to burn the fuel is called an oxidant. Rockets can operate in the vacuum of space because they carry their own oxidant. The oxidant is kept in a separate chamber. Some oxidizers rich in oxygen are hydrogen peroxide H2O2 or nitric acid HNO3. When the fuel and oxidizer are carried in separate chambers, the system is called bipropellant rocket. When the fuel contains its own oxidizer and is stored in a single chamber, the system is called a monopropellant rocket. Monopropellant rockets require very safe handling. Pumps are valves. The fuel and the oxidant are supplied in controlled quantities to the combustion chamber by the pumps. Engine or combustion chamber. The fuel and the oxidant are forced together into the engine where they react together. The burning of the fuel in the presence of oxygen produces hot gases. The exhaust or the nozzle. The fuel burnt in the combustion chamber produces hot gases. These gases are ejected backwards from the exhaust at very high velocities through a small opening called the nozzle. This is action. As long as the gas continues to stream out from the exhaust, the rocket will continue to fly. This provides the reaction which lends the forward thrust to the rocket. Payload. A payload is a scientific instrument or a space vehicle or a satellite carried by a rocket. It is usually placed in the nose or cone, the front portion of the rocket. The ratio of the payload mass to the fuel mass of the rocket is called the payload ratio, or payload ratio is equal to payload mass m by fuel mass m. The outer frame. The streamlined shape of the rocket helps to reduce the air pressure and heat due to friction when it crosses the dense layers of the atmosphere. The outer frame of the rocket is made of heat-resisting materials. The fuel burnt in the combustion chamber of the rocket produces hot gases. These gases are ejected with high velocity through a small opening called nozzle at the exhaust. This is action. The release of hot gases provides reaction, which lends the forward thrust to the rocket. The acceleration of the rocket depends on the mass of the rocket m, the rate of the fuel consumption r, the velocity of the exhaust gases v, exh. The thrust of the rocket, force is equal to mass of the rocket into acceleration of the rocket, that is equal to m into a. Also, thrust is equal to rate of the fuel consumption into velocity of the exhaust gases, that is equal to r into vex. The mass of the rocket includes the mass of the propellant and the payload. There are other practical aspects that need to be considered. 1. As the rocket consumes fuel at every instant, its mass goes on decreasing. 2. Further, the acceleration due to gravity changes continuously as the rocket ascends. 3. The atmosphere offers resistance in the lower strata of the atmosphere. The escape velocity. The minimum velocity which is required for a body to escape the gravitational attraction of the Earth is called the escape velocity. The escape velocity of Earth is about 11.2 kilometers per second. It's very difficult for a single rocket to attain this velocity. To overcome this difficulty, multi-stage rockets are used. Several rockets are joined together one on top of the other to provide the necessary power. Rockets built in this way are called multi-stage rockets. First stage of the rocket. The first stage of the rocket is the largest in both the dimension and weight. In the beginning, rocket should be given sufficient velocity to rise to prescribed height. After reaching a height of about 100 kilometers, the first stage gets detached. The fuel required in this stage is about 60 times more than that required in the third stage. Second stage of the rocket. In the second stage, the rocket takes over the task of producing further acceleration. The mass of the rocket is reduced as the propellants and the engine of the first stage is discarded, thereby increasing its efficiency. This helps in the second stage to carry rocket to the greater height compared to the first stage. Third stage of the rocket. The velocity of the rocket increases with every stage. The third stage then launches the satellite or the spacecraft. A satellite of mass m revolves around the Earth in an orbit of radius r. The radius of the Earth is r, e, while its mass is m, e. The orbital velocity of the satellite is v, o. The gravitational force of attraction between the Earth and the satellite provides the necessary centripetal force. The gravitational force of attraction between the centripetal force of the Earth and the satellite is gme m by r square, that is mvo square by r. Hence, VO is equal to square root of gme by r, that is square root of gme by r plus h, where g is the gravitational constant, which is 6.67 into 10 to the power of minus 11 Newton meter square per kg square. VO is equal to orbital velocity. M is the mass of the Earth. R is the radius of the Earth. H is the height from the Earth's surface. All slow-moving projectiles fall back to the Earth. Rockets used for launching spacecraft have to overcome Earth's gravitational traction. We have already learned that the escape velocity is that minimum velocity with which a body must be projected so that it escapes from the gravitational field of the Earth. If a body has to be moved against gravitational force, work has to be done. It can be shown that the work that has to be done in pulling a body of mass m out of the Earth's attraction is equal to gme m by r, where me is the mass of the Earth and r is the radius of the Earth. If the body is projected with a kinetic energy greater than this value, it escapes into space. The escape velocity VE is therefore given by half m VE square, that is equal to gme m by r. Therefore, VE is equal to square root of 2 gme by r, which is square root of 2rg. The escape velocity is independent of the mass of the body. In case of the Earth, escape velocity is 11.2 kilometers per second. Relation between orbital velocity and escape velocity. Orbital velocity VO is equal to square root of rg. Escape velocity VE is equal to square root of 2rg. Therefore, VE is equal to square root of 2VO. Launching of artificial satellites. Multi-stage rockets are used to launch artificial Earth satellites, as in figure 6.4. At start, the rocket must be given sufficient velocity to rise to the desired height. When it has ascended to the required height, the satellite in the last stage is placed into the orbit with sufficient horizontal velocity. If the velocity is greater, the satellite moves into a larger orbit or escapes from the Earth's gravity. If the velocity is lesser than the proper value, the satellite falls back to the Earth.